So on to the photoelectric effect. Which really, in my view, laid the foundations down for quantum mechanics, quantum physics. So the idea is that if you have a metal plate, and that was a thought experiment suggested by Einstein, if you have a metal plate and you shine light on that metal plate, now we have to talk about, you know, what kind of energy this light has, what kind of frequency, what kind of wavelength. The energy in the light is hc over lambda. Now think of this, hc over lambda, we're talking about visible light, right? Order 3, 4, 500 nanometers, something like that. Not very energetic, right? What happens when you reduce the wavelength of light? You get something more energetic. The light that has a large wavelength does not penetrate deep. So this is interacting with the surface electrons. Once you go from visible to, let's say, X-rays, you get into another kind of interaction between light and matter. You get Compton scattering. Beyond that, you get per production, and there is many different, you know, ways with which radiation interacts with matter, and we use these to either image or treat or what have you. So yeah, you can look that up, interactions of light with matter or radiation with matter, and there is a whole 4th-year courses in nuclear physics on that you can take as an option if you want. Right? Now this light comes in, and this is a photon, right? Comes in, and you know, you have electrons sitting here. This is a conductor, so there is free electrons in there, and some of these free electrons are surface electrons sitting, you know, right at the surface. Some of them are more bound to the metal than others, depending on where they sit exactly and what's going on in there. But let's say the light comes in, and what Einstein said we would notice in this thought experiment, or this experiment, is if you were to shine light of a large wavelength, right? Let's say, I don't know, whatever, depending on the metal you have, wavelength is like 800 nanometers or so, you'd see nothing. There is energy coming in, but you'd see nothing, right? Nothing would happen. And then if you decrease the wavelength, suddenly, when you decrease it to a certain point, you'll see electrons pop out, okay? And I ask the question, okay, so how come you had to decrease the wavelength to get them to pop out? Right? So that's you know, a very important part of the discussion on the photoelectric effect. Right? So okay, fine, that's one part. Okay, now why can't we just, like, remember in waves we have intensity, you know, the intensity of a wave is proportional to power, proportional to energy, really. Okay, so right, intensity is, remember, from waves we have I is equal to P over 4 pi r squared. And power is the rate at which you get energy. I mean, it's just, you know, say it quickly here, energy over time. So really, if you increase the intensity, you should be increasing the energy. And if I increase the, you know, what's going on here is that these electrons are sitting in a well, they're bound to the metal, they need a certain amount of energy to get out. There is 2 arguments here. One is if we just wait long enough, like in waves, if you keep supplying energy to something, at some point, you know, I'll soak up enough energy, and then, you know, I can leave, I can go, right? That wasn't happening. The other thing that was interesting is that, so increasing the intensity, if you increase the intensity, right? And intensity, as I said in the previously, just a few minutes ago, or the previous video, you increase the intensity for light, means you increase the number of photons, right? As we'll see in a minute. The implications of Einstein's hypothesis here, right? Or thought experiment, because you do that in the lab now, right? If you increase the intensity, right? So these electrons need a certain amount of energy to come out, right? And if you wait long enough, nothing's going to happen, despite the fact that light is coming in. If you increase the intensity, nothing is going to happen. But if you decrease the wavelength, then electrons get emitted. Right? At a certain point, you reach a certain wavelength value, you reach a certain value for the wavelength, and then electrons get emitted. And once these electrons get emitted, if you increase the intensity, what increases is not so, what you notice also is that, okay, so you emit the electrons, you keep decreasing the intensity, the kinetic energy of the electrons that leave here, you have electrons that go this way, and the kinetic energy, if you decrease the wavelength of the light coming in, the kinetic energy increases. And if you increase the intensity, this is interesting, the kinetic energy does not increase. That does not happen, but if you increase the intensity, the number of electrons going out increases. And that is here your proof that light is made of photons. Okay, so, and there is another thing in there, in that, another quantum effect here, in that the electrons sitting there, if you don't hit them with the right energy, they won't come out. They're not just going to sit there and soak up the energy and leave, right? So the conclusion from this is that light is indeed made up of photons. You increase the intensity, you increase the number of photons coming in, which increases the number of electrons coming out, but each photon has a certain energy. The energy of the photon is given by hc over lambda, and this is not energetic enough yet, but you decrease lambda to the point where the photon has enough energy to kick the electron out, and then you keep decreasing the wavelength, which means you have more energetic photon coming in. More energetic photon coming in means the electron has, more kinetic energy to go out. Okay? So now, how do you measure the kinetic energy of these electrons coming out? Well, you pass them through, a cathode and anode. So let's say you have, positive charges here, and this is hooked up to some sort of variable, voltage source, and you can measure the current. Okay, so you can measure. You have a voltmeter. You have a. You can change the potential difference. You have a variable power supply, and you have an ammeter that measures the current. So what happens is these electrons leave and they come in, and some of them have more kinetic energy than the others. Some of them are dragging behind, and they're coming in, and you're measuring current. You're measuring current going in. So you start dialing up the potential difference. You're starting dialing up the power supply, and as soon as an electron goes in there, it becomes more drawn to the positive charge, repelled from the negative charge, and the weaker electrons kind of fall out of the equation, and the more energetic electrons still make it, until you get to the point where you hit a certain value for the voltage where no more electrons come through. And this is the point where the kinetic energy of the electron, Ke, the most energetic electrons, Ke max, that's how we know, what the most energetic electron energy is. You keep cranking up the voltage until you get to QV, which is this is your electric potential energy. It is the charge times the potential difference, or Q delta V. Okay, this is delta U. So you keep cranking up the potential difference until no more electrons come through, and that's when you've hit the most energetic electrons. Right? For an electron, this is what Ke max. The charge of an electron is E multiplied by V, and V is called V stop. That's how you measure the energy of these electrons. Right? We're gonna pause here and continue with the second part of the photoelectric effect.